idea for today is see how we can unlock the potential of OTP, proven strategies for application development. In short, the idea of this talk is see some advices, some tips and tricks about how we can empower our applications, our Elixir applications, if we use the goodnesses of OTP. That is the idea. But first thing first, a little of introduction. I'm Alvaro. I'm from Uruguay. I am computer engineer, and I've been working with software for 10 years, mostly in backend. In my last projects, I met Elixir, and I completely fell in love with this awesome programming language. So hopefully, I will be investing my upcoming years in this great language. I work as a staff engineer at YWork. YWork is an Uruguayan-based technology company that offers services using Elixir, Ruby on Rails, among other technologies. And in terms of my hobbies, probably the thing that I enjoy the most is to travel, meet new culture, new people, taste new food, and that is a little about me. This will be the agenda for today. We're gonna start talking a little about OTP, then how processes work in Elixir, and then our three main modules for today, and this is task, agent, and Gen server. Okay, so OTP, let's tackle this. What is OTP? So OTP stands for Open Telecom Platform. It's the Erlang framework or system that we can build reliable, concurrent, and fault-tolerant system, and then it was inherited by Elixir. It was developed by Ericsson, one of the leading telecommunication company in the late 80s and early 90s. But do we really know which was the motivation behind the creation of OTP? A little of history about OTP. So it was the year 1980, and the telecommunication industry was facing significant challenge in building systems that needed to be highly reliable, scalable, and capable of handling massive concurrent operations. In those days, traditional programming languages and systems was struggling to meet these demands efficiently. In response to these challenges, a team at Ericsson developed Erlang. So basically, Erlang was designed to support concurrency, fault-tolerant, and distributed computing natively. As time went by, and as Erlang matured, the need for a standardized framework and set of tools for building complex applications emerged. And this finally led to the creation of OTP, which encapsulates best practices, design principles, and reusable components for building reliable systems. So that was, in short, the history of OTP. And I also think that from time to time, it is good at least to know where the things came from. Finally, we can say that OTP core is Gen server, while agent and task are high-level abstractions. So what this really means? So Gen server was created in the first place for OTP. On the other hand, while agent and task are not part of OTP, strictly talking, they both follow the same functionality and way of working of OTP, so we can say that they both adhere to OTP. Okay, that was a little of OTP, so now let's see a little about how actually processes work in Elixir. So in Elixir, the unit of concurrency is a process. A single process will always be sequential and can only attend one message at a time. So this means that, for example, if a single process receives several messages at the same time, then that process can be a potential bottleneck for our applications. Also, it is good to know that Elixir processes are different from OS processes. In fact, Elixir processes are much lighter than an OS process and are handled by the Erlang virtual machine, the one that will be using scheduler to manage the lifecycle and execution. We can also say that processes are isolated from each other, so this means that a crash in one process wouldn't take down another process, since processes don't share any memory between them. Also, in terms of the garbage collection, we can say that it takes place at process level. So we avoid the situation of stopping the entire system, cleaning, and retaking execution. And the consequence of this is the fostering responsiveness. And by the end of the day, processes are just mailboxes communicated through message sending. So this means that if a single process receives 2 messages at the same time, one message will be attended for the process, and the other one will go to the process mailbox. Okay, so let's take a look at this picture. This is actually how the Beam, the Erlang virtual machine, works in terms of the operating system level and the hardware. We can see that the entire Beam is running in only one OS process, and we will be using OS Stress to manage and execute a bunch of Elixir or Beam processes. We can see in the picture that we are going to have one CPU core, one scheduler for CPU core that we have available in our hardware. Also, in terms of the scheduler, we'll be giving a slice of time to each process to execute. And when this time elapses, the process will bow to the queue and wait for its turn to be executed again. This will be repeated as many times as needed until the process finishes its execution, avoiding monopolizing the resources and also avoiding blocking other processes indefinitely. This way of working about the scheduler is called preemptive scheduling and is one of the reasons how Beam can run under very high loads without crumbling. Lastly, we need to bring to the table that since we are dealing with a functional programming language, Elixir, in which functions tend to be of only a few or several lines, the context switching made by schedulers takes place very often, and the consequence of this is the fostering of responsiveness. So, in my personal opinion, if I need to summarize how well works the Erlang virtual machine in only one image, I will say that it is magic, definitely. Okay, let's go to our first OTP module, and this is task. The main goal of a task is to just execute one particular action. This can be to grab data from a database and refresh a cache, or execute some sort of script. We can also say that the task doesn't allow to store state. Probably one of the main differences between a task and an agent or agent server is that the task doesn't allow to store state. And lastly, we can say that the most common use case is to convert sequential code into concurrent code running asynchronously and concurrently. Okay, let's get our hands dirty and see some code examples. We are going to see 2 examples. The first one is to how we can send emails concurrently in different processes if we use the start child. And the second one will be how we can merge the result of several long-running functions before returning the result to the client. Okay? That is the idea of the code examples. What we are going to have here is just a regular Elixir project, no Ecto, no Phoenix, no nothing fancy, just Elixir, a supervisor, and us, okay? The first example that we are going to see is the notification sender. The goal of this module is try to send emails in different processes in a concurrent way. So for this, we are going to have a function called send notifications. And what this function is actually doing is iterating through that email list using the enum.each, okay? And then for every email, we are going to use the task supervisor start child. So what is doing the start child? This function will be spawning a new process, this is a new task, for every email that we are going to be sending the email. And this is actually great because in terms of the fault tolerance, if something goes wrong with a task, then the supervisor can take some action according to its restart strategy. But we need to take into account that here we are not linking the current task, the current process, to the current module. Here we are providing a specific supervisor to supervise the task module, okay? So for that, in the main children, for the main application, we need to add that task so we can use this task for manage the lifecycle and execution of those processes, okay? This is also great to use when we need to perform, for example, side effects and we don't care about the result. for example, send notifications can be a good case to use, okay? That being said, we are going to be sending the emails to those users, and in this case, we are going to be just logging the email address and inspecting the PID to see what is actually going with those processes, okay? That is basically that's the idea. So let's give this module a try. We are going to just copy and paste the module name and execute this function, send notifications. Okay, so what can we see here in the console? In terms of the concurrency, here we can apply parallelism because we can see that every email sent is being made in different processes. And also, this code snippet is quite useful, for example, when we need to turn sequential code into concurrent code. That can be a possible use case, okay? That is for the first example. So let's see this second example. Imagine that from time to time we have the need to combine the response of several long-running functions, merge it, and return the result to the client, okay? And also imagine that we are going to build, in all the examples, a payment application to send money between users, and right now we are going to use a task to fetch all the currencies that our application can handle, okay? For that, we are going to have this first function called fetch currencies using task. And the idea is to create a list in which we are going to have an anonymous function, and every function will be fetching the currency from a different source, okay? So imagine that we have a team that is distributing around the world, and one team is storing the currencies in a database, one team is storing the currencies in a file from this that is in a server, and the last team is building an API call, so we need to make an API call in order to fetch the currencies, okay? This is the idea of this list of anonymous functions. So then we are going to have the task assign stream, the one that will be receiving an enumerable. This is the list of function. And then for every function, we are going to be calling the anonymous function. So just to have an idea, the output of assign stream will be a stream of tasks that will be executing concurrently on every element of the enumerable, in this case the function of the list of function, okay? Since the assigned stream will be returning a stream of result, we need to process that. For that, we are going to be using the enum.map, so this will be iterating through that stream. And for every element, since every task is returning a tuple with the atom OK and the list of currencies, we're going to be applying this pattern match so we can extract the list of currencies that every function will be returning to us, okay? After having this, since enum.map is returning a list, we are going to have a list of lists because every function is returning a list. For that, we are going to use list.flatten so we can apply data structure to use. And finally, we're going to store the currencies in a cache. Just to have an idea, every function that you are going to be using here is just a simulation, so we can just focus on what is important to us. But to simulate that logic, we are going to add a process of sleep. So the database, for example, will take 3 seconds, go into the file on this 4 seconds, and finally make the external API call will take 3 seconds, okay? Also store the currencies in a cache will be logging the final result that the client will be receiving, okay? That is for this function. But also we are going to have this function called fetch currencies without using task. The goal of this function is exactly the same. We are going to be fetching those currencies, but in this case we are going to be executing this code, let's say, in a regular way without using the goodnesses of a task. So this will be sequentially. We are going to be executing this function. After this is finished, the second one and the third one, okay? Finally, we are going to just merge those results and return the result to the client. That is the idea for the function. So what we can do here to compare the two results, we are going to be making kind of a live benchmarking, and we can compare the final output of one function and also the other one, okay? So we can make a comparison between the result of using a task and not using a task. Okay, so in the left part, we are gonna fetch the currencies, but using the task. And in the right side, we are gonna be fetching the currencies, but without using the task. So let's go for it, okay? We can see that in the left part, the part that is using the task is already finished. The final time that this will be taking is 4 seconds because it's a function that is taking the most. In the right side, we can see that the overall time will be 10 seconds because we need to finish, to wait to all the operations are finished, and right after we are going to be returning the result to the client. We can also see that using task, we are applying concurrency because every function is being making in a different process. On the other hand, we are using the same PID, and this is because we are executing the code sequentially. So what is the moral of this example of a task? Imagine that if in this very naive, straightforward, and simple piece of code, we can boost more than 2 times the final time. If we use these kind of tips and tricks in our entire code base, then the final output of our software can be of a much better performance and responsiveness. That is for the task module. Okay, let's continue with our next friend, and this is the agent. So an agent is just an abstraction around state. So the main goal of an agent is just to store state, and then can be return that state in other part of our application. It's allowed to store state and retrieve the state via simple API. We are going to see that just using agent.update to store the state and agent.get to retrieve the state is enough to have a process that can manage state. And also, we're going to see that if we add long-running functions, if we add heavy operation in the synchronous function of the agent, then the client can be blocked, and this is obviously not a very good design, okay? So let's see some examples. We are going to see how we can store and get state using an agent, and also we are going to be adding some heavy logic in the agent.get, and let's see how we can solve that situation, okay? We are going to be returning to our grades payment application to send money between users. And now we are going to be using this module called currency store, okay? The main objective of this agent will be to just store all the currencies that our application can handle, okay? We can see that here we are using the use agent statement. So this is under the hood giving us the child spec function, so we can add this module under a supervisor. This is what we are actually doing here. We are adding this as a child of the main application supervisor. And then we are going to have 3 functions. The first one is the start link. This is the function that will be actually creating our process, our agent, and we need to provide the initial state. In this case, we are going to just give it an empty list because we are not going to be storing any currencies after the agent is started. And then the module name, this will be the current module name that we are going to be working here, okay? Then we are going to have 2 functions. Add element, this is just adding a new element in the list of currencies. And then the get element, the one that will be returning the current state of the agent, okay? That is the idea of this agent. Let's give this module a try so we finally can understand how this is actually working. For example, if we execute the get element, there's no currencies yet because the initial state was an empty list, but we can also, for example, add a new currency in our agent. We are going to add the currency from Uruguay, and if we execute the get element, we can see that this is returning a list of 1 element. But let's see, for example, what happened if in the agent.get. Instead of just returning the state, we are going to make an external API call or something that will take some time, and we need to return the agent state, but also concat new currencies, okay? So in this case, we are not going to just return the state, but we are going to make it, we're going to be making an external API call, the one that will be taking 4 seconds, and right after, we are going to be returning the result to the client, okay? So in this case, we are going to add, again, a new currency. Right now, we have only 1 currency. And if we execute the get element, the one that will be returning the result to the client, we can see that now we are making that heavy operation. We need to wait 4 seconds until the function is finished, and after we are going to be returning the result to the client. Are the clients happy being blocked for 4 seconds? Probably not. So one possible workaround for this is to take that heavy logic, the one that is blocking our process, move to another function, move from outside of the agent, make that heavy computation, and then return the result to the client. This way, we are not blocking the agent anymore. But hold on, because since we are not working inside of the agent, another process, let's say process B, can be modifying our agent state, and this can lead to race condition. Okay, so what we are gonna do here is execute a piece of code that will be simulating that situation. We are going to be moving that heavy operation outside of the agent. We are going to be retrieving the agent state. Another process will be modifying our state, and then we are going to be returning the result to the client. Okay, that is the idea of this piece of code. We can start checking if our agent is empty. There's no currency. We are going to add a new currency in our agent state. So right now our agent is including 1 currency. Okay, so let's execute that function and store our final result in this variable called state. So here in the console we can see that we are getting the current state of the agent. We are doing that heavy operation, the one that was previously blocking our client. In a different process, another logic is modifying our state, and then finally we are going to be returning the result to the client. In our variable, we can see that actually we are only returning 1 currency to the client, but the source of truth, our agent, has 2 currencies. Okay, so what is the conclusion of this? If we add heavy operation inside the agent can be blocked. We can move that heavy operation outside of the agent, but hold on, because if another process modify our state, we can be returning an outdated version to the client about our agent. Okay, that was for the agent. And finally, my favorite one, Gen server. So what is a Gen server? A Gen server is a module for implementing the server part of a client-server relation. We can also see a Gen server like a regular web server, in which we are going to have different clients. This is different process, sending requests to our Gen server, and then the server will be returning back a response to those clients. We can store state and build complex logic in the Gen server. Apart from storing the state, we can also execute synchronous and asynchronous logic, and this is very useful, for example, when we need to build long-running services. And also, we are going to have a wide set of callbacks available to implement, and we are going to see in a minute those callbacks. Okay? Okay, so finally see some code. We are going to use stored and get state so we can understand how a basic Gen server works. We are going to see what happens if we add heavy logic in the Gen server startup, and we are going to solve this situation using the handle continue. And then we are going to be building a Gen server that will be storing some state, but also we're going to be executing some cron job that from 5 seconds to 5 seconds will be sending messages from within the Gen server. Okay, that is the idea for this final example. So Gen server, we are going to have this module called currency store, and let's say that we are going to be continue making this payment application, but we are moving from the agent because we need to perform some kind of logic that the agent is not, doesn't allow to us to execute. Okay, so right now we are going to be using the Gen server to store all the currencies. How we can organize the code of a Gen server? For me, one of the best approaches is to organize the client part of the Gen server or the public API function, and then the server part or the internal callback function. Okay. In terms of the client part, we are going to have again the start link. This is for creating the Gen server process. In this case, we are going to just put an empty list as the internal state. and then the name will be the current module name, okay? Then we are going to have two functions, add element to add a new currency in our agent server, and then get elements to return the internal state of the agent server, okay? This is a way to send messages from outside of the agent server. Then we have the internal callback functions, or the server part of the agent server. We are going to see the init function. In this case, since we are not modifying the internal state, we can just return the tuple OK state. And then we're going to have two callbacks, handle cast, the one that will be managing the asynchronous call. This is for add a new element. And the handle call, the one that is synchronous to get the element of our Shen server, okay? That is the idea of this Shen server. And again, let's play a little with this. If we execute the get element, we don't have any currencies yet. We can add a new element, a new currency, and if we execute the get element, this is returning a list with one currency, okay? So, situations that can happen when we use a Shen server. Let's say that we don't want an empty list as the internal state. We want to make an external API call. That API is not working very well, it's taking 4 seconds, and right after we are going to be returning that state, the one that is being building in this heavy operation after 4 seconds, okay? So let's start our Shen server. Again, we can see that we are blocking the startup of our Shen server for 4 seconds. This is obviously quite by design, so that kind of things we cannot be making in the Shen server. What can be using instead of just adding a heavy logic in the start link? In a Shen server, we have a very useful feature that is called the handle continue. The handle continue Shen server callback is something that we can use to defer the initialization of the Shen server, but without blocking the process initialization. And this is basically what we need to do here to solve this situation. We're going to have here this Shen server called currency store with post initialization. Great name. It's exactly the same server. We can see that if we follow the cycle organization, we can see that we are going to have the client and then the server part. This is very similar, but now in the init function, we are going to be adding the tuple continue making API call. So this tuple will be triggering the handle cast. This is the one that will be going to move that heavy operation that is making our Shen server block. So in the background, let's say our Shen server will be executing this heavy operation, but probably our Shen server will be not blocked anymore, okay? This is the way that we can use a heavy logic to add to our Shen server, okay? So again, let's give the Shen server a try. We are gonna add in this Shen server as a child of a main application supervisor, and we are gonna start the Shen server. We can see that in the console, this is executing the API call, the one that was previously blocking our Shen server. We are gonna be making that heavy operation, but the Shen server is not being blocking anymore. In the meantime, I can continue executing some code, but in the background, this is executing that heavy operation. This way, we are not blocking our Shen server, okay? Right now, so far we saw 2 ways of sending messages. This is from outside of the Shen server using call and cast. But using the Shen server, we have another way of sending messages to a Shen server. This can be seen also as internal messages. And for that, we can use process.send or process.sendAfter, okay? Again, this is quite the same Shen server, but here we are going to be doing 2 things. The state of the Shen server, we are going to be storing the amount of successful and failed transactions. For that, in the initial state, we are going to be storing a map. And the second logic that we're going to be working here is we're going to try to execute from time to time, from 5 seconds to 5 seconds, some logic so we can update that internal state of our Shen server, and the counter can be updated from 5 seconds to 5 seconds, okay? Again, the code organization is quite the same. We have this function update state instead, in case we want to replace the current state of our Shen server, and again, the get state to return the current state. Then in the init function, here we are adding the send after. So what is doing the send after? This will be sending a message after some time, after 5 seconds, and the recipient will be the PID that we are specifying here. This is the self function. This function is returning the current PID. So the one that will be receiving the message will be the current send server. And after 5 seconds, we want to execute the function called update transaction counter. Here we are going to be handle these kind of messages using a new callback. This is the handle info callback. And here we are going to add that logic that we previously mentioned, the one that will be checking for new transactions and update the current state of our server. Okay. Here we have this function called getFinishedTransaction. This is just a dummy function that will be returning a random number for the transactions that finished with successful and another number for the transaction that actually finished with an error. Okay. Having this new counter, we are going to just be updating the current state of our server. We are going to be updating the current counter of the finished transaction. And then again, we are going to be saying to the server, hey, execute this logic again in 5 seconds. This way, we are going to be creating kind of a cron job inside our server. Okay? So again, we are going to need to add the server in the main application supervisor, and then we can just go ahead and give this server a try. In the log, we can see that we are setting to check for transactions every 5 seconds, and 5 seconds to 5 seconds, this will be updating the transaction counter. Okay, so right now, if we go to the console and execute the get state, we can see that we have the counter, but after 5 seconds, this will be updating the counter. So this way, we know how we can store state in a server. We can know how we can send messages from outside of the server, and also we now know how we can send internal messages from within the server. So far we know how we can execute or turn sequential code into concurrent code using task. We can also store state within a server, but if let's say we have some simple logic, maybe an agent is enough, but if we figure out that the logic is quite complex, then we can move and create a server. Okay? So let's sum up and reflect about the topics that we learned so far. OTP, build fault-tolerant, scalable Elixir apps with predefined modules and tools. With processes, enable scalable concurrency via lightweight isolated units. With the task module, handle asynchronous operation easily for concurrent execution. With the agent, manage state simple and safely within Elixir processes. And finally, server, simplified stateful process implementation with a consistent API. So before closing this presentation, I want to give you all a phrase that sort of fits this occasion. Unlock the true power of Elixir you will, if OTP you master. Thank you for being here and have a great rest of the day.